Welcome to conservation of energy. Energy cannot be created or destroyed. It can only be transferred from one form to another. Let's look at the different types of energy we can conserve and classify them based on what we see. Energy is the ability to cause change. Even in English, this is true. If you have no energy, I'm not going to get any work out of you, am I? You are going to lie there in bed or on the couch like a lump, and that is not going to change until you get some energy. What sort of changes is physics talking about? Well, let's take a look. You can't change an object's, let's see, you can change its electrical voltage. If it's a trick phone, you can change its temperature and its potential for hazard. You can change its motion. If you hurl it across the room, you can change its location. You can do work on it and change the amount of damage it suffers. You can blow it up with TNT and change its chemical makeup, or in extreme cases, you can change its very existence by nuking it to kingdom come. Each of those we're going to quantify as a different type of energy. Let's start at the top. Ask yourself the question, is it moving? If the answer is yes, you've got kinetic energy. Add the question to your note sheet. First thing you're going to ask in every stage of the problem, is it moving? It is very common for you to do work to gain kinetic energy. You could look here and see Yamamoto doing work. There's the force, there's the displacement in the right direction, and he is giving the ball his kinetic energy. That's the result of him doing the work. If it's moving and you need to know how much kinetic energy it is, the equation for kinetic energy is 1/2 mv squared, where m is the mass in kilograms, and v is the speed it's going, or the speed you want it to go. If you want to transfer kinetic energy into another type of energy, you can do that. You can use kinetic energy to do work, especially if you're in the Demo-Olympics and you're trying to demolish something.
Commence the Demo-Olympics and subsequently demolish this entire massive building. Let's quickly talk about how to demolish an entire massive building. Because when most people think of building demolition, a lot of times they think of this, a giant wrecking ball. And while wrecking balls can weigh up to 12 tons and they look really cool, they're really most effective against concrete and brick buildings because they crumble. But steel doesn't crumble, it just bends and deforms. So even the largest wrecking ball will be no match for our 25-story steel building.
Is it moving? If the answer is yes, it's doing its wrecking by kinetic energy. Mark Rober has just told us that kinetic energy isn't going to be enough for his purposes, so let's see what else there is out there.
Commence the Demo-Olympics.
Eventually, we'll discover that there is rotational kinetic energy. We'll answer the question, is it spinning, and add a formula onto that. I am going to pretend I didn't just fess up to this because we are going to discover rotational kinetic energy organically over the course of our classroom and lab demos. Next type of energy is gravitational potential. Ask yourself the question, does it have room to fall? If it has room to fall, it's got gravitational potential energy. Add to your notes. If it has room to fall, it has enough gravitational energy for n, the mass in kilograms, g, the strength of the gravitational field, 9.81 meters per second squared, and h, the height in meters. Most medieval technology worked on gravitational potential energy. Catapults, trebuchets, anything where you drop something heavy onto something and launch what it is you're going to launch by something falling on it, there is gravitational potential energy. Speaking of storming the castle and destroying things, what about that wrecking ball? It was moving, but not enough to bend the steel.
But steel doesn't crumble, it just bends and deforms. So even the largest wrecking ball will be no match for our 25-story steel building, which means we need a lot more energy. If you look really closely, you can see the equivalent energy of 20,000 sticks of dynamite right here. It's just in the form of gravitational potential energy.
The top of the building doesn't have room to fall.
Really up high in the air.
I would never have thought of destroying the building under the work done by its own weight, but that's why Mark Rober is the master engineer, enemy of torch pirates and scammers everywhere.
if you were somehow able to weaken the building in key spots, especially at the bottom, maybe by using some explosives, the building would start to fall and crush itself under all that weight. This is why the fastest and cheapest way to make a building not exist anymore is to let gravity do all the work for you over a couple of really exciting seconds.
For the
And then
full
spend the next
local
couple of
video
months
on
cleaning
General
up all the
Olympics,
debris on the ground.
check Canvas. There is more than one type of potential energy. There's also elastic potential energy. Ask yourself the question, is it stretched? Most medieval technology that did not work on gravitational potential energy worked on elastic potential energy. The Katniss's bow is not stretched. It doesn't have the potential to fire. But if it is stretched, all she has to do is let go, and the elastic potential energy of the bow will be transferred into the kinetic energy of the arrow. If she's done the work to draw that bow, she can fire the arrow with as much kinetic energy as she had elastic potential energy. How much is that? Spring potential energy, 1/2 K. That's our old friend, the spring constant from Hooke's law in Newtons per meter, and X, the stretch distance or draw distance of that bow, of that spring, of that elastic you're working on. Archer Jim Kent, a.k.a. Grizzly Jim, is not only a master sportsman and huntsman, he's also the guy you may see doing a lot of these super cool stunts in Hollywood, or coaching the actors how to handle elastic potential energy in longbows, crossbows, and anything else that they have to operate on screen for historical martial arts, contemporary awesomeness, and contemporary hunting. He's got lots and lots of examples on YouTube on how to operate bows and arrows, and how to make the best use of the elastic potential energy that you have, as well as the physics of projectile motion and drag that you learned about earlier in the semester. How to make the arrow lighter, Eastern style, and get it where you're going to deliver the potential to do a lot of damage. With those types of energy, we are going to have enough problems to last us the rest of first semester. Teachers and educators call this kind of stuff mechanical energy. Mechanical energy is just shorthand for kinetic and potential. Is it moving? Does it have the potential to move if you knocked it off the shelf, or if you launched it somewhere? Rube Goldberg machines tend to work on kinetic and potential energy. The potential for something to fall, the fact that it's moving and can hit something else. The heavier that brick is, the more gravitational potential energy it has to deliver when it falls. And if you look, you will see things stretched at the ready, giving other things kinetic energy when they are unstretched by way of launchers. There's lots of mechanical energy here, but I'm also noticing this machine is kind of noisy. That's going to be a problem for physics formulas. Ask yourself, did it make a noise? If it did, there is sound energy. Specifically, friction did work. You can see the displacement of the bow. You can see it moving back and forth in the right direction, as friction does work to convert kinetic energy into sound energy. If there's friction, there's going to be sound energy. There is no formula for sound energy. Sound energy is vibrational. It's stored in the motion of the molecules making vibrations in the air. You can't convert sound energy into any other type of energy. Once that sound is made, it creates a pressure wave in the air. That sound disperses, it spreads out. You're not getting it back. If that's what you wanted because you're building speakers, great. But even those speakers have useful sound energy, which is the music you're playing, and not useful sound energy, which is the buzzing you hear in the background on this video and any other type of electronic sound making. I hate that buzzing. Sound energy is typically a bug rather than a feature. It is an unwanted byproduct of whatever it is you're doing, even if whatever it is you're doing is trying to make a specific and beautiful kind of sound. If there's friction, there's not just sound energy, there's also thermal energy. You know that there's a certain amount of thermal energy you can make for yourself simply by rubbing things together. Put in your question column in your notes, was there friction? If so, there is thermal energy. This is the second law of thermodynamics that you heard of in chemistry last year. The work done is equivalent to the change in heat of the system. If you want to start fire because you're a survivalist, you can do this on purpose if you have experience, training, or have watched on YouTube the proper technique for making enough friction in the right place to start some smoke by heating up the dry grass you serve as kindling. The rest of the art is moving the kindling to an actual bonfire so you get the fire that you need. The thermal energy in a less useful form is where all that kinetic energy went when the force of the crash did work, changing the front of the car from the front of a car to a piece of crumpled metal. There was a tremendous amount of sound and thermal energy. We name this after the sound energy. We name it a crash. But there is both sound and thermal energy, taking all of the kinetic energy and converting it into something you can't use. For what it's worth, they have tried to use it. We're going to talk a lot about runaway truck ramps and how they save truckers from disaster when their brakes fail in the mountains. This is one of the few I've seen that haven't been pulled off of YouTube for sheer idiocy, where not only is the truck going up a ramp as it tries not to spin out of control, but they put things in its way. They put steel nets in its way to convert some of that kinetic energy, not just up the ramp, here we go, here we go, here we go, but into the sound energy and thermal energy as it pulls those steel nets in. Me personally, I think the ramp is going to do a better job, which is why there's only one of these videos and dozens of examples of truck ramps converting kinetic energy into potential energy all over the Rocky Mountains. If you have two things touch and there's friction between them, you're going to make sound energy and thermal energy. We're going to have to take that into account. All of that will take us the rest of first semester. Because we don't have formulas for sound and thermal energy, we're going to group them. We're going to call them internal energy. Internal energy tends to be the end of the process, the unwanted byproduct that you're going to have to account for, assuming you don't have a perfectly frictionless, levitating something or other in a vacuum. Second semester, we will meet electric potential energy. That's a real easy one to spot. Is it plugged in? Are there batteries? Is it charged? If it's charged, if there are batteries, you will find that energy is power times time, and the power formula we'll learn second semester depends on the electrical current I, the voltage V, and there's your time that you've left it on. If something is electrically charged, you can do very fun things with kinetic energy and not have to worry about friction because of the electrostatic repulsion of like charges will get you a frictionless environment. Look at that beautiful quantum levitation, no friction, using magnetism and electric potential energy to solve the problem of two objects touching. You know what else works on electric potential energy? You do. Your nervous system works on sodium and potassium gated ion channels that transfer positive and negative, periodic table. They're both positive. Potassium is positive and sodium is more positive. That will transfer more positive and less positive, or at least positive in a different place, signals all the way down from one end of your nervous system to another. That's how your brain sends signals to the muscles to move. We'll do more on your body's potential to do cool things in a minute when we get to chemical potential energy. Ask yourself, is there fuel? Don't make the mistake of associating fire with thermal energy. You can have thermal energy even if you don't have fire. But fire is an oxidation reaction between the fuel and the combustion of the oxygen in the atmosphere. If there's fuel, you are actualizing the potential in the chemical potential energy. Your car runs on chemical potential energy. You run on chemical potential energy. Cross-country runners know that the night before a big meet, you are supposed to have a big pasta dinner, lots and lots of carbs. Simple starches have chemical potential energy that is very easily accessible. The word you learned for this in biology was adenosine triphosphate, ATP. Specifically, the acids in your stomach, in your digestive process, break the chemical bonds in your food. This is really easy to do with simple starches. They move the energy around as they reform bonds in other molecules, and they transfer those other molecules, the sugars, to your bloodstream. When your brain gets the signal through your nerves to the muscles saying it is time to move, 3, 2, 1, go! Your muscles, when they receive that electrical signal, break the triple bonds in adenosine triphosphate, leaving behind ADP with only a double bond, and they use that chemical potential energy to make your muscles move. If you're feeling the burn, it's because you're running low on, or you're running out of ATP, and your muscles have gone to anaerobic respiration, which is a different, anaerobic means no oxygen, method of getting chemical potential energy. It has an unwanted byproduct that's kind of acidic, and that's the burn that you feel. If you can take a breather and do some stretches and get a rest, your body can clean out that acid, get some more ATP. Hopefully you've tanked enough on pasta and energy drinks before the race that you've got plenty and to spare to see you through to the end of the course. The formula for chemical potential energy is the one you used in chemistry class. The heat that you'll get from that chemical potential energy actualized is directly proportional to the mass, the specific heat, and the change in temperature that's going on. So, if you are very, very ill-advisedly trying to make homemade solid rocket fuel using chemical supplies you can get in hardware stores, you can, if you don't mind third-degree burns and spatter, convert that chemical potential energy of the substance you made into kinetic energy. Notice the little bits of flaming material spraying everywhere, and even the YouTuber saying, I'm out of here. How much energy can you get? Well, that depends on the mass of the rocket fuel, the specific heat of the rocket fuel, and notice you are expecting a very large change in temperature. The other thing that everybody knows runs on chemical potential energy is your car. Here are the spark plugs, creating a spark in a chamber filled with gasoline fumes. The exploding gasoline pushes the piston up, and the low pressure causes it to contract. A typical engine has 4 cylinders as the explosion comes in and the exhaust comes out, giving kinetic energy to the pistons in your engine. Next question, is it glowing? Is there light? If the answer is yes, there is radiant energy. Plants work by radiant energy. Photosynthesis takes the radiant energy of the sun and uses it in a chemical process, converting it to chemical potential energy as the plants store sugar, starches, and grow. Then we feed the plants and we get the chemical potential energy. Solar panels work on radiant energy. Remote control, anything with an electric eye, works on radiant energy. LEDs work on radiant energy. And the formula you saw in chemistry class, the energy is directly proportional to the frequency big peace sign thing that looks like a V. What's the constant of proportionality? Planck constant. Next question, and a dangerous question it is too. Does it have mass? Well, everything has mass. Do you plan to use the mass? Do you plan to destroy the mass by nuking it to kingdom come? If so, how much energy would you get? Here's the most famous formula in all physics, E equals mc squared. If you get down to the subatomic level inside protons and neutrons, you will find that positive charges are glued together in the nucleus by the strong nuclear force. It's called the strong nuclear force for a reason. If you try to separate individual parts of protons and neutrons, you will get a tremendous amount of energy. You will not be able to break apart a proton or a neutron. If you try to break apart protons and neutrons in a very big nucleus that is too big for its own good, it's going to look something like this. E equals mc squared is incredibly useful on the atomic and subatomic level where neutrons and protons decay through radioactivity. Do not do this on anything bigger than a proton, or you will be making Hiroshima and Nagasaki. The tokamak, the tevatron, the Large Hadron Collider in Switzerland, all of these are doing E equals mc squared at the subatomic level to study physics and not to nuke anything. The reason that nuclear weapons have the potential to destroy the planet and destroy the human race, unlike up through 1944 chemical bombs, is that C is 3.0 times 10 to the 8th. That's already 300 million meters per second squared. Now square that, and you're going to get 9 times 10 to the 16th joules in one tiny little kilogram of plutonium. Convert that kilogram of plutonium into energy, you're going to have Fat Man and Little Boy, and you're not going to have the cities of Hiroshima and Nagasaki. You're also going to have every survivor within 200 miles getting cancer and leukemia from the radiation poisoning. This is rest energy, the energy it has by just sitting there minding its own business. Please do not use it for anything if it is bigger than a proton. Even neutrons are a little bit heavy for safety. The last item on this list is dark energy. When I was in 11th grade physics, this was not on the list, but the 1992 WMAP study looked at the cosmic microwave background radiation, mapped what we can see in the universe, and confirmed without a shadow of a doubt that just because we can't see it and we can't feel it doesn't mean the energy is there. Dark energy is what's describing the expansion of our universe. The fact that infinity now is bigger than infinity used to be, but not as big as it's going to be in the future. Dark energy is a property of space-time. It describes how our universe is growing. You can think about everything getting further away from everything else like a balloon expanding or a loaf of bread getting bigger as it's baked and it rises. Consider there are bigger infinities and smaller infinities. This is the forefront of contemporary physics. This is where we are now. Dark energy is one of the coolest things we can possibly research, and I'm looking forward to your generation telling me where it came from, how it works, and how to describe it. Now, let's put all the vocabulary words together. Work is the change in energy. If the problem asks you how much work is done, ask yourself, what kind of energy is changing? How much of it is changing? All of it? Do you have a formula for that? Use the formula. If you did 10 joules of work, you're going to have 10 joules of kinetic energy. If you use half of that for potential energy, you're going to have 5 joules of each. If you want to know what force to use to do the work, or what displacement you need to get the work done, force dot displacement, that is, force times displacement in the correct direction, will give you that change in energy. This is the work energy theorem. Check the change in energy first, worry about force and displacement in the right direction afterwards. Another good vocabulary word to know is power. Power is work over time, aka the change in energy over the change in time. Power is the rate at which energy is changed, the rate at which work is being done. A more powerful entity does the same work, only faster. The units that we're going to be working with will be units of Newton dot meters for energy, but you don't have to say Newton dot meters. 1 Newton dot meter is equal to a joule, and a watt being a measurement of power, change in energy of change in time, 1 watt equals 1 joule per second.